Welcome to the first lecture. Here we are going to derive Reynolds Averaged Navier Stokes equation. And we are going to derive this for incompressible flow. For the incompressible flow, we can write the Navier Stokes equations as follows. Where rho is the density of the flow and nu is the viscosity. Okay, this is kinematic viscosity. U is the velocity. Remember that this is a vector, and P is pressure. This is a scalar. And the second equation is the continuity equation, which is the divergence of velocity is equal to 0. In order to derive Reynolds Averaged Navier Stokes equations, we have to perform Reynolds decomposition. In Reynolds decomposition, we decompose any flow variable, an average value and its fluctuation. Similarly, the flow variable P is decomposed into a mean value and its fluctuation. This is the step 1. Now we substitute this decomposition into the Navier Stokes equation. We can write. So after substituting this Reynolds decomposed variables into the Navier Stokes equation, we'll take Reynolds average of these entire equation. So we can write as follows. So this is denoted as an overbar. Let me talk briefly about Reynolds averaging operator. For any variable phi, which is the function of space and time, I can write the Reynolds average value of this, which is nothing but a time averaged value, as limit t tends to infinity, the integral t plus capital T phi x comma tau d tau whole divided by t. Given this, we can see that the variable is averaged over a certain time interval, which is capital T. Capital T should be large enough such that the turbulent fluctuations are well captured. Now let's see some of the properties of Reynolds averaging operator. So number 1 is linearity. So this particular operator is linear. So if you apply, let's say we take a scalar a and b, two scalars a and b, and two flow variables phi and psi. So if we apply this Reynolds averaging operator over this particular function, then we can, since this is linear, we can write this as a times phi bar plus b times psi bar. Secondly, the mean of a constant is constant. That means if we take an averaging of a constant, we'll get this constant back. Number 3 is if we apply this Reynolds averaging operator on a average quantity, we'll get this average quantity back. Number 4 is very important, which is if we apply averaging over a fluctuation, we'll always get 0. And number 5 is something that will also derive, that if we apply this averaging over a product of two flow variables, then we'll get this plus the average of the product of these fluctuations. So let's see how we can apply these properties. Using these properties, we can derive the averaging of this particular equation. So let me write this again first. We'll handle this term separately. Now since this particular operator is also linear, so this averaging will go inside and we'll get u bar, and since the bar of bar is again u bar and the bar of the fluctuations is equal to 0, then we get this term plus u dot grad u bar is equal to, similarly here we'll get p bar of bar over rho. Rho is constant for incompressible flows, and similarly nu times del square u bar of bar, and for the fluctuations this will be 0. So therefore we'll get, now let's see the non-linear term, which is the convection term. So for the convection term we can write so the averaging of this entire thing, which is equal to, let's simplify this, the averaging of this all four terms, which will equal to the averaging of these individual terms. For the first term, since both the terms are already averaged, we'll get this term as it is, plus we'll get this term times the average of the fluctuation, which is equal to 0, and similarly this average of this times the averaging, which is again equal to 0, and the last term, which is the average of the fluctuations, which will remain there. So you can see that as we have seen the property, the product of two flow variables, the averaging of product of two flow variables is equal to the product of the averaging plus the averaging of the fluctuations. So let's write the combined equation again. So we'll get this plus the averaged convective term and the averaged pressure term, averaged viscous term, and an extra quantity, which is, so this term we can also write as the divergence of this particular tensor. So we also define Reynolds stress tensor as tau r is equal to negative of rho u prime tensor product u prime, the average of this. So therefore we can write this term as equal to 1 upon rho divergence of Reynolds stress tensor. So therefore the final equation we can write as, clearly on the derivation of Reynolds averaged equation we get an extra term which is an unknown, the Reynolds stresses. So therefore this leads to a closure problem, and to remedy this various models has been proposed. So some examples are k epsilon model, k omega model, etc. As you have seen in introduction of this particular course, that we are going to go through these models and then learn how we can use these models in OpenFOAM and solve various problems. We'll also see that how different models leads to different solutions and which model should be used in what kind of simulations. Thank you.